In the previous video, we started looking at how to evaluate limits at infinity algebraically. And as mentioned in that video, what we're going to do is look at special types of functions and see what process can be applied to evaluate such limits. And so far, we've done the polynomials and we've done rational functions. Now we're going to take a look at algebraic functions. Right? And what does it mean for a function to be algebraic? Well, it can be not it can be, but it is a combination of polynomials, or in fact we could say rational functions. But then in these algebraic functions, you can also have roots. So what I'll say is, instead of trying to write down a general algebraic function, which is harder to do than say a general polynomial or a general rational function, this is what I'll say. I'll describe this type of function in terms of what operations you'll see in this function. So what you'll see the four arithmetic operations. So addition, subtraction, multiplication, and division, and also you will see roots, right? And that's supposed to be an n, because it doesn't have to be a square root. It could be a cube root, fourth root, any root, right? So an algebraic function, along with your variable x, and other constants and so forth, or constants, you're allowed to perform these operations. And again, what we want to be able to do is to evaluate their limits at infinity, see if they exist, right? So we'll do a couple examples of the algebraic, and that way, when you see the examples, you'll see what type of function I'm talking about, and then we'll describe the process. Now, so let's start with number one. So let's say this is our function. It's 12x plus 25 over, right? So nothing new so far. But now in the denominator, let's put a root. Let's put the root of 16x squared plus 100x plus 500, right? So, for instance, if the function just had 12x plus 25, that would be a polynomial. If the function had 12x plus 25 divided by 16x squared plus 100x plus 500 without the square root, then it would be rational. With the square root, it's now called an algebraic function, right? So let's compute two limits for this function. Let's compute the limit as x goes to positive infinity, right? And then after that, we'll do the limit as x goes to negative infinity. So let's take the limit of this. Now, there are several approaches that you could take with a function like this. I will illustrate two of those methods just for the first example here, and then for subsequent examples of this type, we'll just use one of the two. But I want you to see several ways, at least a couple ways, that you can evaluate this. Here is the formal way. Now, similar to what you will do with the rational functions and the polynomials, you can divide this expression by a certain power of x, right? The trick is, though, is in identifying what that highest power of x is, you have to take into account now the square root, right? The square root essentially cancels out with this power of x So really, if you think of just the square root of 16x squared, then the square root and the square would cancel out, and you'd be left with the first power of x. So that's actually what you're going to divide. You're going to divide each term by x, right? So let's do that. And remember, this is the first of two methods, right? So maybe what I'll do is go here, and this method, what we're going to do is divide the top and the bottom by x. Right? Now keep in mind that x is positive. That's going to play a role as well. So I will have the limit as x approaches infinity. So dividing this by x, the 12x by x gives me 12. Dividing the 25 by x will give me 25 over x. Now the denominator, because the entire denominator is under a square root, if I divide the bottom by x, it's going to look like this. 16x squared plus 100x plus 500, right? So it's going to look like that. Well, over x, so like this. Why did I write a 5? So over x. Now, in order for us to get the x under the square root, I have to use a little trick or a little property. Maybe a property is a better word. And here's a property that we're going to use. If x is greater than 0, then x can be written as the square root of x squared, right? That makes sense. So what I'm going to do is replace this x with the square root of x squared, and you'll see why in a second that is helpful. Right, so we got 12 plus 25 over x. And now I have two roots. I'll give myself a little bit more room. So we'll have the square root of 16x squared plus 100x plus 500, and then all over the square root of x squared, right? And it looks like we're making this thing way more complicated than it needs to be, but eventually it will work out, I promise, right? So here's another property of roots that we will make use of. If you have the square root of a over the square root of b, that can be written as the square root of a over b. So what I can do is, instead of having two separate roots here, I can put the whole fraction under one root. So we have the limit as x goes to infinity. And then in the numerator it stays the same, 12 plus 25 over x. Now we're going to write one big root. So all over the square root of, and now put the 16x squared plus 100x plus 500 all over x squared, and then reduce that, right? So basically this is what we can do. Take the 16x squared, divide it by x squared, that leaves 16, plus take 100x, divided by x squared, that gives you 100 over x, and take 500 divided by x squared, that gives you 500 over x squared. Man, now why is this form helpful? Because now we have the same property that we used in those rational functions that says each of these terms that I am circling in red, as x gets very, very large, they all approach 0, right? And that was the whole point of trying to, figure out first what is the highest power of x, and then using properties of roots several times to get a single root in the denominator where either the terms that are left are constants or there are terms that have a positive integer power of x in the denominator, so that x gets very, very large. These terms approach 0. So what's our final answer? So now that we can evaluate it, we can stop writing the LIM, and we're left with 12 plus 0 over the square root of 16 plus 0 plus 0. So that's 12 over the square root of 16, which is 12 divided by 4, which is 3. All right. So now let's so again, we got an answer of 3. Let's go back up here, and I'm going to show you a different way, right? Which is equivalent to what we're doing, but it is a lot more efficient, right? But we will still have to make use of this property. So whichever method you decide you're going to settle on, right? It's not you won't be able to avoid using properties like this and this. And there are more general properties of this that we have to keep in mind if it's not just a square and an x. What if it's like a x to the 4th and then an x squared? Or what if there is a square root of x to the 6th? So we have to think of those properties in general, but here is the alternative method. The alternative method is to focus on the dominant terms, right? So using dominant terms, and we can do this because it's still just powers of x, right? So using dominant terms, right? Now let's highlight those dominant terms. In the numerator, this is the dominant term. In the denominator, under the root, this is the dominant term. So, and again, whenever we have a limit at infinity, we can identify the terms that are going to dominate the other terms. The constant never changes, right? But as far as things growing larger and larger and larger, the 12x grows the largest in the numerator. The 16x squared grows the largest in the denominator, so that's what we're going to focus on. So my next step, I can say, well, that limit is equal to the limit of 12x over the square root of 16x squared. Now look at the left, look at the left, right? This was our first step after dividing through by x. Now look at the right. A lot simpler, right? But okay, well, let's see how it goes. So next up now, see what is helpful about using the dominant terms is you turn long, complicated expressions into monomials. Again, a monomial is an algebraic expression that has just a single term. So by just focusing on that one dominant term, you get to ignore all the other ones. Right? So we got 12x. Now here, this is again where we use this fact. And you might say, well, isn't it always that the square root of x squared is equal to x? No, that's only true if x is positive, right? X could be a negative number, and then when we do the limit as x goes to negative infinity, you'll see how you have to adjust your thought process here. But in this case, what I will do, I will write this as the square root of 16 times the square root of x squared, using the same property there. Now what I'm going to do is replace the square root of x squared with x. It's kind of ironic. On the left-hand side, we replaced the x with the square root of x squared. So on the left-hand side, we went this way. On the right-hand side, we're going to go back the other way. Right? So replace this root with just an x. So we have this. So the numerator is still 12x. Now in the denominator we have 4x, and look at that. The x's are common factors. And we're left with 12 over 4, and the same answer is 3. But I think when you look at these steps, compare it to this, right? Much less work, but it's algebraically equivalent. So essentially what we've done is by applying, again, this concept of dominant terms, we pretty much were able to focus or eliminate the terms that we knew would go to 0, and again, focus on the terms that dominate the top and the bottom, right? And then with our nice property of roots, we're able to reduce it to 3, all right? So that's what happens when you, so again, those are the two options. And don't be surprised when I say this, but there are some students that actually prefer using the more complicated method, right? So now let's with the same function, let's do a limit as x goes to negative infinity, right? So I'll rewrite the function, that way I don't have to keep scrolling back up. So let's do the limit as x goes to negative infinity. Now from now on, I'm going to choose one of the methods, and for efficiency, I'm going to continue highlighting how to use this dominant term approach, right? And then we have our root there, and then we have the same 16x squared plus 100x plus 500, right? So now using dominant terms, right? So by dominant terms, this limit is equal to this limit. Again, it's the same first step. So the top term that dominates, it's 12x. The bottom term is the root of 16x squared, right? And then the first property of roots, that's also the same as it was above. So x going to negative infinity, and we have 12x, and then this is the square root of 16, which is 4. But I'm going to write this as the square root of x squared, because now I'm going to show you in general what is the proper simplification of the square root of x squared, right? And this is an important property. The square root of x squared in general reduces to the absolute value of x, right? Because it could be, in other words, you could start out with, like, in fact, let me show you what exactly, just kind of illustrate what this property is saying. If, for instance, you start out with 5 squared, and then you take the square root, you would expect to get back the original, right? The original 5. And that's exactly what would happen. But what if you were to do negative 5 squared and then you compute the square root? Shouldn't you also get back what you started with? Right, so you should technically get back the negative 5, right? And that's exactly what this property is saying. And the reason why it works out this way is this. Remember how the absolute value function is defined. It's a piecewise function, right? And many times that's overlooked. But the absolute value of x is defined as x whenever you plug something that's greater than or equal to 0, it's just going to return the same value. If you plug something negative in, it's going to return it as negative x, and that's whenever x is less than 0, right? So in the first example, when x is going to positive infinity, that's why we were able to replace the square root of x squared with x. But now, because x is going to negative infinity, which is less than 0, we're going to have to simplify the square root of x squared as negative x, right? So this is right here where the difference is, and it's because now my x is going to negative infinity and is therefore negative. So the square root of x squared reduces to negative x, right? And that's the only difference in the solution. But it comes back to this key definition, right? And then, so we got this. So we have our 12x, and then we have 4, and now it's times a negative x. And I'll just go across here and finish it up. So what happens is, when the x reduces, I now have a negative 4 in the denominator. So this is the limit as x goes to negative infinity of 12 over negative 4. So this function, as x approaches negative infinity, approaches a value of negative 3, right? So let's just write a sentence kind of summarizing everything that we've done. So since the limit as x approaches infinity of our original function is 3, and the limit as x approaches negative infinity of the original function is negative 3, this function has two horizontal asymptotes, one at y equals 3 and the other at y equals negative 3. Right, so f of x has horizontal asymptotes at y equals 3 and y equals negative 3. It doesn't always work out that way, right? It doesn't always work out that way. It just depends on what type of root and whether you have to apply this property or not. All right, let's try another example of this so you can see another example of the algebraic type of function. All right, and I won't make this one too complicated, but let's say, so number 2, let's say the function is now the cube root of x to the 6th plus 5x to the 4th plus 1 over 3x squared plus 9x plus 1. Right? So let's say this is our function now, and it has a cube root as opposed to a square root. Right? And let's compute both limits again, and let's see what's going to happen. So let's do our limit as x goes to positive infinity of this, right? So cube root x to the 6th plus 5x to the 4th plus 1 over 3x squared plus 9x plus 1. And what I'm going to do, let's do the dominant term method again. So by dominant terms, that limit is equal to this limit. Well, the dominant terms are really easy to identify. In polynomials, you have the x to the 6th there, that's under the root, and then you have a 3x squared there in the denominator, right? So it's equal to the cube root of x to the 6th over 3x squared, right? So then we have to simplify the cube root of x to the 6th. Now, the cube root is a slightly different function than your square root, right? However, what you can always remember to do is, and this works well, is you can express your root as a fractional power. So for instance, if you have the cube root of x to the sixth, this is x to the sixth to the 1/3 power, and then you use that other property of exponents where you multiply the 6 and the 1/3, so that's going to give you x to the 6 over 3, which is x squared, right? So that's what this simplifies to, right? And we don't have to worry too much about the negative stuff yet because x is approaching positive infinity, right? So this x squared is now in the denominator. Sorry, oh, I forgot to write my limit. I can't do that. Right? That's poor communication if I do that. So it's the limit as x goes to infinity, and then you have x squared in the numerator, and then 3x squared in the denominator, and lo and behold, x squareds cancel out, and then you have the limit of a constant. So you have the limit as x goes to infinity of 1/3, which is equal to 1/3. All right. So now what does it look like if we change the positive infinity to a negative infinity? Right? Now the thing is, so let's do this. So we have the limit as x goes to negative infinity. Now it's a cube root, and you end up with so I'll go ahead and write down the dominant terms first. So right here, so basically skip to this step. Right? And we have to think about this for a second in terms of what is the cube root of x to the sixth if x is negative, right? Well, the cube root, because it's now an odd power, it's a little bit different from the square root, and it has this particular property. So in fact, let me write both of them down. So if your x is greater than or equal to 0, then I'll write it in several ways. The cube root of x cubed will be x, right? So this is the basic one where the root completely cancels out, right? If x is negative, it turns out that the cube root of x cubed is negative x, right? And this is why, because if x is negative, then x cubed is a negative number, right? And the cube root of a negative number is also negative. So you're going to end up with negative x, right? Oh, actually, no. That's not right. If x is negative, then the cube root of x cubed is still going to be your x, right? And so if we now square this, so we can add this and say the cube root. So if we now have x to the sixth, and we're taking the cube root of that, that is equal to x squared, right? And then also the same whenever if your x is less than 0. So the cube root of x to the sixth. Because if x, see what happens is if x is negative, when you raise it to the sixth power, it becomes positive, and then you end up getting this same result back. So in this case, because of the cube root, this step is exactly the same. The cube root of x to the sixth will simplify to x squared regardless of whether x is positive or x is negative, right? So this step here, there's no difference in it as opposed to what happened with the square root where there is a difference. So we end up with x squared, and we still have 3x squared in the denominator, and then this simplifies and reduces and simplifies to 1/3, right? So in this case, this function has only one horizontal asymptote. So therefore, f of x has a horizontal asymptote at y equals 1/3. All right. So with the algebraic functions, it's really important that we have these properties of roots understood to where we can apply them, right? And a lot of it has to do with whether it's an odd root or versus an even root, and then sometimes there's a difference when your x goes to negative infinity versus positive infinity. So those are the key things that you need to keep in mind with these limits of algebraic limits at infinity of algebraic functions. Right? In the next video, we'll continue to look at limits at infinity, and then we'll turn our focus to exponential functions and logarithmic functions. See you then.